Hello and welcome to another episode of EnVisioneering Exchange, the podcast where industry leaders discuss the most important topics in sustainability, climate change, buildings, and urban efficiency. I'm Vic Marinich from Danfoss, and I'm delighted to be your host of the podcast. You can subscribe to our show on Apple Podcasts, Spotify, Captivate, or wherever you get your podcasts. Today we have Jeff Staub, Sales Director at Danfoss Climate Solutions North America, here to talk to us about cold climate heat pumps. Jeff, thanks for taking the time to join the show.
Vic, thanks so much for having me on. I really look forward to a couple minutes of detailed exchange on cold climate heat pumps today. So thanks again for having me.
Absolutely. So maybe before we jump right into the good stuff, how about can we talk a bit about your background and how you got involved in HVAC and heat pumps?
Yeah, sure. It goes back quite a few years. I started back as an engineer in our design center for thermostatic expansion valves in our facility down in Mexico. And that design was specifically for residential air conditioning systems. So back in 2003-04, we started on a design project for this new air conditioning valve. And it couldn't have come at a more timely impact, where the EPA was changing legislation, moving from SEER 10 to SEER 13 at the time in 2006. So as we qualified the valves and started working with our air conditioning customers, started getting into residential air conditioning and support for the equipment manufacturers. And then going from there, just 4 years later, changing over from R22 to 410A with the phase down of R22 due to the Montreal Protocol. Again, an entire new redesign for all of the residential air conditioning manufacturers. And then it's just been the evolution since of increased standards, going towards HSPF or heat pumps. And then, of course, where we are today with another generation of refrigerants coming into the marketplace, and now more and more of a focus onto the heat pump side. And rather than just looking at holistically the cooling side, integrating both the cooling and the heating side and looking at northern climates as well. So really 20 plus years now working with residential air conditioning and heat pump applications.
You bring up a really good point. We've done a few podcasts already on heat pumps, and I think maybe different people have different definitions of what heat pumps are. So just to kind of level us out here, typically when we talk heat pumps, we talk about here in the US reversible systems, right? So they do cooling in the summer, heating in the winter, and most of them here in the US, we're talking about air to air. So your typical unit you have outside the home. And even though it's a new topic, heat pumps have been around forever. I mean, I remember previous home down in Richmond putting in heat pumps in the 90s, right? And I was just looking the latest AHRI data. The market has sold almost 2 million units so far this year, which is over 42% of all the residential units sold are heat pumps. So even though it's kind of the hot topic, this is a product that's mainstream. It's been around a long time already, right? So it's not something new under the sun. But what is kind of new is what we want to talk about today, and that's the cold climate heat pumps. So can you maybe kind of talk about what is a cold climate heat pump and why do we need them?
Yeah, so exactly that. Cold climate heat pumps, you're exactly right. When we talk in this context about cold climate heat pumps, it's the reversible air conditioning systems. Reversible for residential or for commercial packaged and rooftops. And in that state, we've been using heat pumps for years, but typically in a traditional reversible air conditioning system that we deem as a heat pump, it can be used pretty much in the lower 2/3 of the United States. And in the lower 2/3 of the United States, you get your heating, but you're much more focused on the cooling aspect of keeping the house cold in summer. In the winter, typically what you're going to do in those colder days, you're going to put in an auxiliary heat system, strip heaters, electric resistance heaters, or you could go with a dual fuel gas system to really compensate for that missed capacity in the heat pump under your sub-freezing temperatures. Cold climate is exactly that. You're trying to completely eliminate the use of auxiliary heat or emergency heat, the electric heat strips, so you can use the capacity of the heat pump in much, much colder temperatures. So we know in the northern parts of the United States, you're getting up -10, -20 degrees Fahrenheit, very cold temperatures. It's hard to get the capacity or the heat out of that air. So cold climate heat pumps, exactly that. How can we get this efficient use of transferring heat from the outside air into the building to heat the house without using straight COP1, auxiliary heat, or emergency heat strips?
And I think on top of just the emergency heat strips, right, it's getting rid of that natural gas in the furnace too, right?
That's exactly it. I think heat pumps have been limited in the northern climate because exactly that. It's in these colder temperatures, so much of that is driven by natural gas furnaces, oil-fired furnaces. So to reduce overall greenhouse gases and reduce carbon emissions, driving towards something where you're not creating heat, you're transferring heat at a much more efficient level, you can optimize that with a cold climate heat pump.
Yeah, and it's not just right for those people that are looking to, say, have a greener solution and are looking to get away from natural gas, right? Some of these things are actually legislatively driven, right? That we're going to have to start at least thinking about in the future.
Yeah, and that's been the transition. So I think we can look at today, we can look at roughly 7 states have now adopted legislation, maybe not fully at the state level, but at local jurisdictions. It actually started at some local jurisdictions, Berkeley, California. They actually adopted a carbon ban, or let's say a fossil fuel ban on new installations in 2020. We can see that different municipalities in Maryland, in New York, so many municipalities adopted it in New York that the entire state, they've implemented a statewide ban. And they're coming at different rates. We know that Washington, D.C. will have a ban in 2026, New York State for different size buildings in 2027 or 2029. So we can see there's a trend and an evolution. And although you can say, oh, it's just 7 states, the reality of the impact of those 7 states is that's over 25% of all of the natural gas consumption for heating systems in the United States based on the population. So it's a heavy impact on that.
Right. Because most of those 7 states are in the Northeast. And obviously that's where you need to have the heating. And just make sure everybody doesn't jump out of their seats here, right? This only pertains to new construction, right? I mean, if my furnace dies tomorrow and I live in one of these states, I don't need to go out and convert to a heat pump, right?
That's exactly right.
All right.
It's funny. You look at that, and I think people believe that the federal government has a heat pump Gestapo that's going to come in and take your gas-fired furnace. So it's a situation where, yes, your old furnace dies, you can replace it. Now, you will have the option to go and cost compare a furnace versus a cold climate heat pump, because the technology is there and it's growing today. But it is, I think, the bans, all of the bans that are coming, it's for new construction only. But anybody out there that has a current furnace, you can replace that with a furnace, or you can go with a much more efficient cold climate heat pump.
All right. So if you've got natural gas in the house today, oil in the house today, and you've got the product failed, you can replace it like for like, right? Going forward. So that's,
absolutely.
Yeah. So I think that's important to know, because that would certainly make things tougher on the homeowner. So heat pumps have been around a long time. Right now we're hearing about cold climate heat pumps. So what is it that drives suddenly what's making these things so relevant today?
Today, I think it's a progression of technologies as well as overall efficiency. How much are you paying for your fuel bill? We know with gas prices on the increase, that's having a more direct impact on each homeowner in their monthly bill. So when you look at efficiency, and also the legislative demand is going to drive that. So as more and more jurisdictions, states adopt natural gas bans, that's also going to drive the technology.
So as you said, right, we're getting the stick part with this legislation driving the change away from natural gas to electricity. But how about on the carrot side, right? I think the federal government is doing a few things too to help pull the technology forward as well, right?
Oh, absolutely. So there are, and I wouldn't just say the federal government, I would say, you could say tax returns. You can say that the utility companies are offering rebates, and local jurisdictions are offering rebates. So some in the form of the direct purchase of the equipment, a rebate on the equipment, but also tax reductions.
And as for the technology itself, right? I mean, the federal government is helping the different manufacturers also develop these products as well, right? Because today there's not a big market there. And so I think if the OEMs tried to develop this product on their own, it maybe wouldn't be the most cost competitive solution, right? But there's also incentives on the manufacturing side, right?
Absolutely. So the federal government has implemented for almost the last decade several challenges, started with commercial heat pump challenges, high efficient heat pump challenges, to the 2021 cold climate heat pump challenge implemented by the DOE, and now into the commercial cold climate heat pump accelerator program that they have. So that's an evolution of technology. And I think our government has always supported that with Oak Ridge National Laboratories. It's not just, hey, we're going to do this to subsidize heat pumps because we want to drive in that direction. Our federal government has an entire area of just looking at research and how do we promote new technologies and new research into the market. So I think this is an area where we have 10 manufacturers that have signed up for this cold climate heat pump challenge. They're at various different stages. I believe 8 of them have already passed the internal laboratory testing and are now completing their field testing, their 1 and 2 years in cold winters, in Maine, in Idaho, in South Dakota. So you have these areas where the equipment manufacturers, they're monitoring the equipment. They can see that there's 15 to 20% reduction in the energy consumption. So that's a direct benefit to the end consumer on their utility bill.
I think it's a neat partnership there with the federal government, right? Because it's not a manufacturer out there trying to convince somebody up there in North Dakota, hey, no, trust me, I'm going to put this thing in and you're going to stay warm and it's going to save you some money. But it's the federal government finding people to support this 2-year testing out in the field. It's finding the utilities to do the measuring, right, and everything. So it's really done on the up and up, and we've got good results, consistent results, and it's not technology or manufacturer specific. It's kind of across the board. So I think that's, been a really good partnership going forward. But you talked a little bit about new technologies. I mentioned before, heat pumps are around 30, 40, whatever it is years, but we've never had cold climate heat pumps. So what's changed in the last few years that now make cold climate heat pumps even viable?
There's quite a few different technologies, and you can borrow technologies from, you could say, different market segments. For instance, if you look at large chillers, they've used economizer systems or intercoolers for many, many years. Subcoolers, I think that's being adopted at smaller levels. You have to fundamentally look at what we consider to be the heart of the system, which is the compressor or the pump of the system. And the compressors, looking at the compression ratio that's needed, essentially your lowest ambient temperature to your indoor temperature that you're trying to achieve. The lower that outside temperature, the more work that you're putting into the compressor. Not only more work, that's more heat and a higher compression ratio. Traditionally, compressors haven't had the capability to handle such a high compression ratio, nor have they been able to handle and deal with all of that motor heat coming out. You burn up the oil into the system. So I think the implementation, both of variable speed compressors, but also vapor and liquid injection on the compressors themselves. A liquid injection helping to actually reduce some of that internal heat to cool the compressor motor, but having vapor injection, really looking at the quality of refrigerant entering into that evaporator, increasing the capacity of the overall system. So helping reduce that compression ratio by having this intermediate pressure is less work on the compressor. And again, I think one of the differences with cold climate heat pumps and overall furnaces is we're not creating heat. So in a gas-fired furnace, you're burning fuel to create that heat. Where here in a heat pump, we're transferring heat. So you have a much more efficient item that's pulling heat from the coldest temperatures outside, compressing that up to a much higher temperature to be able to reject that heat and heat your house. So the technologies and compressors have really grown. And to be able to marry that with variable speed or variable frequency drives to where you have these peaks, very similar in the summer when you have that peak cooling day on the hottest days of the year, you're going to have these peak heating days where your compression ratio and your work is very, very heavy. So you need to be able to size it for that. But how often do you actually operate at that day? So in your cooler days, could still be cold outside where you need heat. You can slow down the operation of that compressor and match the work input needed to the load of the house. So you get a much more efficient operation with a variable frequency drive, as well as pairing that with a vapor or liquid injection compressor to match the demands of a cold climate heat pump.
So if we talk variable speed and then we talk either vapor or liquid injection, do either of those technologies help on the cooling side of things, or is this purely something on the heating side?
Oh, they absolutely help on the cooling side. The same as I said, you have this peak heating day, you have a peak cooling day. And that peak cooling day, when you put into an economizer into one of these systems, an economizer essentially where you're going to gain your extra subcooling for your capacity, but also provide your vapor injection poured onto the compressor. They're traditionally, economizers are used in cooling applications today. So many of your supermarkets have subcoolers, which is an economizer onto it, and chillers today. Most chillers that are out there, high efficient chillers, are using economizers on there to help inject an intermediate pressure into the compressor and reduce some of that load on the compressor. So absolutely, it will help you with your your warm days by increasing the capacity of the system. So again, by increasing that and pairing that with a variable frequency drive, you'll gain some more thermal capacity on the refrigerant side, thereby allowing you to slow down the speed of the compressor and use less work into that compressor on your warmer days.
So for both of those technologies, again, variable speed and economizing, is that something you can add on to your existing air conditioning unit, or do you really need to get a new unit if you're going to, want to go cold climate?
Yeah. So to answer that question, you need a new unit. And that's really the complexity of the compressor to have an intermediate injection port to handle that economizer, but also the entire control system. So yes, there are 1% of the design engineers can go and Frankenstein their unit and retrofit it. But no, for the 99.9% of the population, you have to buy a new cold climate heat pump.
No cold climate kits at your local big box store then?
No.
All right. Sorry, guys, I was trying. So it sounds like variable speed, economizing, those are kind of new. I mean, if you install the unit in your home, everything else kind of look the same? The other components, the other sections, or are you going to see something when you get a cold climate heat pump that's like totally out there?
You'll see it'll really look identical to the units that you have in place today. I think the main differences that you'll see, and you've seen an evolution over the last 15 years, we've seen the outdoor units get slightly larger, and that's for efficiency purposes. That's to reduce the overall, let's say, high pressure or condensing pressure on that compressor, to kind of reduce that work and gain that bit of extra efficiency. So you could see with high compression ratios in cold climate heat pumps, I would expect the outdoor heat exchanger to be a little bit larger, because you're trying to pull heat from -5, -10, -20 degree weather. So you need more condenser surface or outdoor coil surface area, I would say, to be able to absorb that heat.
Yeah. And actually, and you bring up a good point. I don't think we mentioned it before. When we talk about cold climate heat pump challenge, what's cold climate, right? And I think the challenge has 2 temperature programs that the manufacturer can shoot for. Was that right?
That's correct. It's 5 degrees Fahrenheit and it's -15 Fahrenheit.
Ambient, right?
Outdoor ambient. That's correct. And in that situation, the goal for the 5-degree ambient, and typically you say, 5 degrees, it's always 5 degrees outside in the winter where I live. But in general, when we look at heat pumps today, heat pumps that exist today typically have a changeover point of about freezing, 32 degrees. Some operate down to about 25, 27 degrees, but anywhere that you go below that, you're going to be less efficient on the heat pump than you will on the auxiliary heat strips. So you want to make that changeover. But there again, with an electric heating strip, your COP is 1. So your output is exactly what you pay for in your energy consumption. So we want to drive that temperature lower. So in that cold climate heat pump challenge, we want to get to a point at 5 degrees where we can meet the entire capacity demand for a residential house 100% on heat pump without using the auxiliary heat. And the same for, let's say, at -15 degrees, there's a slightly different a standard that you're looking for. But we can see with the cold climate heat pumps today from the 10 OEMs, we can see some of them being able to meet that demand at -5 degrees, where 80% of the cooling is coming from the heat pump, or even down to -15 at 70% coming straight from the heat pump. So you're only in that emergency auxiliary heat down below that -5 and -15 range. So it's a drastic difference in technology when heat pumps today are currently at that 25 to 30 degree Fahrenheit, just below the sub-freezing. And now we're talking ranges of 5 degrees, -5, -15 degrees. So really, really ultra cold temperatures that these cold climate heat pumps will work in.
Right. Today, it's just they start to derate, right? So if you've got a 3-ton unit, you start getting to 25, 20, suddenly you're not getting 3 tons of heating, you're getting 2, 2.5, 1.5, whatever, right? And you're just not able to keep up on the heating mode, right? So the heat pumps will be able to keep that house at your, whatever it is, 74 degree set point, right? Down to at least 5 and in some cases -15. So,
and then that capacity as it derates, you don't have enough capacity to heat the house. So that's where the auxiliary or emergency heat strips come in, the electric heating strips, to make up some of that difference in capacity.
So then maybe the last topic on the designs themselves, the refrigerants, right? There's a lot of talk come 2025 and beyond, lots of changes in refrigerants. 410A seems to yeah, I guess it was at least in our terms a short-lived refrigerant, right? I mean, nothing moves fast in our industry. It doesn't seem like. And 410A was kind of a flash in the pan, right? In and out in not much more than 15 years or so. So is that going to be the same for cold climate heat pumps? Or are they going to be a different refrigerant? Or how do you see it?
I'd say right now for the short term, because the technologies are here for cold climate heat pumps and the natural gas bans in different states and jurisdictions, that's coming. So the technology is here today with economizers, with vapor compressors and variable speed. So for the short term, at least for the short to long term, we are in the refrigerant of R454B. So will that go beyond that? I think that's yet to be said. I believe that there will be further pressures over the next decade, as we've seen in the last 15 years or 20 years since the Montreal Protocol and the phase out of R12. We've seen a complete transition. I expect that to continue. We know that in supermarket applications, GWP below 150 is the target. So you're really driving towards natural refrigerants. In the short term, I expect 454B will be the refrigerant, or R32 based on the equipment manufacturer. That will be the choice of refrigerant for these cold climate reversible heat pumps. If we're talking a decade out, the same as we've done this transition to 454B, which is a slightly flammable refrigerant. If you look overall at the efficiency of refrigerants and you start to look at refrigerants such as propane and other natural refrigerants, they are highly flammable refrigerants, but at the same point, very good thermal efficiency. Does it go there in another 10 years after our industry adopts slightly flammable refrigerants? It absolutely is plausible in the next decade. But I believe that for the short term to midterm future over the next decade, we're here for 454B and R32.
And that's, for those, right, 454B is a makeup including R32, right? It's a blend. And 410A was the same. It was a blend using R32. So all these refrigerants, even though R32 and 454B are both A2L or mildly flammable, they're at the core, they're kind of all very similar refrigerants, right? As opposed to moving to propane, then we're talking, right, something completely different.
Yep.
Yeah, and I can tell you, I've said in on DOE meetings where there's discussions about how do we convert residential to propane, right? So there's a lot of stuff down the pike, but I agree, we don't move fast. So 10 years plus, I think we're good also.
R410A was here since 2010 was the last mandate for the R22 phase out. So 15 years that we're here. So I expect 454 at least the next 10 to 15 years.
That's right. And that 15 years is like warp speed for us, our market,
yeah,
right?
Exactly.
So I think we're probably good for at least that amount of time.
Yeah.
So lots of new technologies, right? Lots of new components with economizers and that kind of stuff and variable speed. Do we have any feel yet on how those cold climate heat pump installation costs are going to be compared with a standard heat pump, or maybe better to compare it since we're talking new construction, like a heat pump plus a furnace? Do we know how it's going to look?
I don't know specific costs. I think we're still very early in, let's say, some of the field tests, some of the launches. I'm sure there are equipment manufacturers that know very well the cost situation. Compared to a conventional heat pump, for certainly, it's going to cost a little bit more because you are adding an economizer, a variable speed compressor into it. So, but I think the difference there is when you look at the basic setup, you have the box inside of your house where you have your blower and your indoor coil, and you have your outdoor coil. In a cold climate heat pump, you add a condenser. Compared to a conventional furnace, you have your indoor coil, your blower, and your furnace on the inside, which you have today, and your outdoor coil. So comparative to a furnace, you're eliminating the entire portion of the furnace. Is that offset by the addition of your subcooler or economizer on the outdoor coil? Probably not. I believe that there's some savings to be had compared to a traditional gas-fired furnace setup.
And again, here we're talking all new construction, right? If you have an existing home that already has a furnace and a heat pump, I guess then actually you could decide also to keep the furnace, right? But doing retrofits is kind of a whole different story here, right?
Yep.
And you would still have access to the natural gas, obviously, as a retrofit.
Absolutely.
Right. So, Jeff, it seems like the cold climate heat pumps are really going to be successful and interesting for everybody up north. Now, if I'm a contractor, am I going to have new tools, new skills? Or what's it going to take to install one of these cold climate heat pumps? Is it going to be very different than what we're doing today?
No, absolutely not. So in a new installation where you have a cold climate heat pump, I think the advantage of it compared to running natural gas lines if there is a fossil fuel ban in that residential, you don't have to install the natural gas lines. From the contractor installing the HVAC equipment, it's very similar to an air conditioning unit today. So it's your electrical hookup, your refrigerant piping from your indoor to outdoor, and then your condensate line. So you just have to make sure that if you're sizing a unit, that again, your wiring size and your disconnect is sized appropriately for the use of this heat pump. But the contractor isn't going to see any other significant changes into it. And that would be so very much on a retrofit. It's similar in your house. If you pull out a gas stove and want to go to electric, you just have to make sure the wire size is there. So very, very similar here. It's contractors, they're installing heat pumps today. 42% of the units are today heat pumps. So you may have a slightly larger unit that in capacity wise, so you need to size that wire size appropriately for that unit, but no other difference for a contractor to install this. Now, what you will have to recognize from a contractor, and very similar as we go through refrigerant transitions and changes, today in the replacement market, there are times where you're just going to replace the indoor coil or the outdoor coil. Not so much going to be able to mix and match that. So when you go to a cold climate heat pump, you're going to have a mated indoor and outdoor coil to install. So the mix matching that you do, very similar today. You can't take an indoor unit from R22 and match that with an R410A outdoor unit or 454B. So there are differences enough that you're not going to mix and match. So but for the contractor, it's no different. If they install heat pumps and air conditioning systems today, you do have the savings of not running the natural gas lines in the buildings.
Yeah. And I have to imagine, since these are going to most likely be super high-end products, they're going to be very smart as well. So commissioning, right, is probably going to be done a lot through the thermostat and electronically and kind of driving stuff that way too, right?
Absolutely. You'll continue to see the evolution of technology and thermostats and integrating into your home and smart home. And you'll see the continual evolution of smart homes and how they connect to your air conditioning and heating systems. And that's not going to be any different with a cold climate heat pump.
Right. Okay. So now costs, hopefully they stay not pretty similar. We've got the different technologies. How is a cold climate now? If I'm looking now and I'm in a place maybe that doesn't have the ban yet, but I can either go cold climate heat pump or let's say dual fuel, a standard heat pump and a furnace. How does the efficiency of a cold climate heat pump compare with that of a furnace?
You'll save about 15 to 20%. So let's look at, let's say, two different ways. When we talk efficiency, you can look specifically at COP efficiency, or you can look at what we're paying with our utility bills. If you look at what we're paying on our utility bills, about 15 to 20% what you would be expected to save over your gas and electric bill versus just an electric bill. Now, when we talk efficiency, a cold climate heat pump is well more efficient than what you have on a furnace. So traditional furnaces, and many that are installed today in the US, are 86, 88%. The best furnaces today running at 98%, which means for 100% of the gas that you're putting into it, you're burning and converting 98% of that to heat. Again, you're creating heat by burning something, but you're still less than a COP of 1 because you don't have full utilization. A heat pump does not create the heat. It transfers the heat from, even though it's a cold outside, inside of the house. So on a COP level, you could see a COP under standard conditions of 3.5 on COP. Under the cold climate, your COP might drop down to 2 to 2.5, but that's still 250% more than COP1. And your gas furnace isn't even there. So you have tremendous efficiency gains on the entire system by going from a gas-fired furnace into a cold climate heat pump.
I think the heat pump challenge said you had to have a COP of 2.4, if I remember right, at the 5 degrees.
At the 5 degrees,
so
that's
again,
correct.
Right, so you're talking 240% more COP.
Correct.
But right, you're saying, so if you're getting rid of that natural gas, so you're going to obviously significantly reduce your gas bill, but you're going to increase the electric bill. But you're saying the net of the two, 15, 20%?
15 to 20% savings on utilities.
Yeah, still something pretty significant for your homeowner when you've got to replace the product anyway, right?
And you can debate all day long whether global warming exists or not. But fundamentally, to reduce greenhouse gases and reduce your utility bill by 15 to 20%. So many people will just look at global warming potential from this is an environmental impact. many in business will say, what's the environmental impact versus what's the cost to implement? And to a homeowner, when you really look at it and say, whether you believe in global warming or not, if you can have an efficiency savings of 250 to 400%, reduce the impact to greenhouse gases by removing carbon dioxide and methane, and also reducing your utility bill by 15 or 20%, it's a huge impact.
Cold climate heat pumps sound awesome. So does that mean you think going forward, are all heat pumps going to become cold climate heat pumps then?
No, I don't think so. There are some savings that you can see on the cooling side, as we had mentioned, in the middle of summer. But when you really look at what is the advantage when you get into some southern or moderate climates, I think a reversible heat pump will do just fine in cooling and heating, but you also have a good portion of the year in both spring and fall where you're not operating that system. Would you put in the additional cost for a cold climate? You would have to weigh that out. I don't believe, though, that with the extra components and going to a vapor injection with an economizer, that'll be 100% of the market. As you said, last year, 42% of all of the residential air conditioning systems were heat pumps today, and they're operating very, very well. Could some of them be more efficient? Absolutely. But it's always a cost benefit of how much additional efficiency gain are you going to get for the amount of cost that you're putting into it. And I don't think you'll see a complete transition to a cold climate heat pump. But for certain, the entire northern half of the U.S., if you're going in that direction of a heat pump, it'll be a cold climate heat pump.
Right. Yeah, and I have to imagine, most manufacturers today kind of have their good, better, best tier of products from an efficiency standpoint. You have the federally mandated minimums and the kind of middle road and the high end. I have to imagine then these cold climates are really going to start at that even higher end, right, when it comes to efficiency standpoint, right? I mean, you're not going to go and get rid of your furnace and then have something that's inefficient there running in the home, right? I mean, so these are going to be even one step higher than those, yeah.
And you can see even on the cooling side, when you look at SEER 2 and the highest tier units, those plus 20, 23 SEER units, they're all variable speed compressors today. So there is a cost basis and a premium for those units. And that you'll see on cold climate heat pumps as well.
Right. So you've already got some of the technology out there. We just add maybe the vapor injection, economizing that stuff, and kind of have a fourth tier, good, better, best, and bester, whatever it's going to be up there at the top.
Yep.
Right.
And we've known of the tiers. And you see that in automotive industry today with the different tiers. OEMs do that today on the SEER rating. I think you'll see more and more of that on the HSPF rating, where you're getting your good, better, and best, and also with cold climate heat pumps.
Yeah, that's another good point, right? Because historically, you buy your air conditioner for cooling, and then, right, if you get heating out of the heat pump, then, right, for some part of the year, awesome. But there was never really a focus on the heating part of the heat pump. But, today, the promotion will be around the heating side, and then cooling will kind of be what it's going to be on these colder ones, right?
Yeah, and I think it's a good evolution that we're in. It's a new technology, and we don't want 100% of adoption of this overnight. That could potentially be disastrous for the electricity grid in the middle of winter. We know that the grid, with the additional work that's necessary to support a cold climate heat pump, if everything in the north today is fossil fuel burning equipment on gas and oil, and that converts to electric, your electric usage and demand on the grid is going to be higher. So having a change in an implementation of many jurisdictions, but 7 states, and taking 25% of that, and that allows for our infrastructure to continue to evolve to be able to support a higher demand or a higher implementation of cold climate heat pumps.
Yeah, and perfect segue to kind of the next question here. So when do you think we'll start seeing cold climate heat pumps available in the marketplace?
They are actually in the marketplace today. So there are manufacturers that sell economized condensers into the market at very low volumes. So if they are meeting, let's say, the cold climate heat pump challenge on residential, they are actively in field testing today, but manufacturers have the technology for cold climate heat pumps. So you will see an evolution of this. It's not like the people in Berkeley, California that implemented the natural gas ban in 2020 that they don't have anything. Okay, they're in southern part of the U.S., so you could say a conventional heat pump will work in that application. But absolutely, the trends are there, and you'll see a constant evolution. But as more and more natural gas bans come in place in 2025, 26, 27, 28, you'll see a natural migration to meet the legislative demands.
So does that mean somewhere off in the future, furnaces and boilers maybe go away?
I don't know that they fully go away. I think that if you look at electric versus gas vehicles, I think there's a lot of people that own 20 and 30-year-old trucks that drive on combustible. I don't think they ever go away. Could there be at one point in the future where there is a legislative ban on fossil fuels? Absolutely. And I don't see that tomorrow or the next day. But going back to 2006, when we first changed SEER from SEER 10 to SEER 13, that was a 30% increase. So we drive towards the overall Montreal Protocol. So regardless of what branch is in the federal government, we can see, even if it's a conservative that doesn't believe in global warming, the technology trends are always going to be there for higher efficiency to drive towards a greener environment. So, and that's without legislative demand. People are technology gurus that drive towards, I want the latest and greatest iPhone. I want to be cognizant of how I impact the environment. So you'll see a natural evolution towards these trends, which means a trend towards cold climate heat pumps away from furnaces. And I think you'll eventually get to a point where cold climate heat pump technology itself will evolve to the point of, at a cost basis, why would you ever want to go with a furnace, gas or oil-fired furnace? So whether it comes mandated legislatively or not in 10 or 15 years to move in that direction at a federal level, or if it just comes through technology evolution, the best technology is going to win out.
Yeah. And I think that if you got a technology with a COP less than 1 versus something that can hit 2, 3 and above, why would you pick the less efficient solution? And I think it's good things like this cold climate heat pump challenge and other things the federal government and the different labs are supporting hopefully helps those manufacturers get the critical mass. And then it's a matter of, like you said, the market deciding, right? I mean, the technologies are there, things are moving, then let the market decide on what they want to go. Perfect. So I think we've covered everything I wanted to talk about. Jeff, I don't know, any last comments you want to make before we sign off here?
Yeah, it's super exciting to talk about heat pumps.
You're one of 6 people in the world that say that, Jeff, but that's
exactly.
awesome.
Exactly. No, it's I can say, working in the industry, I've been a technology guy for many, many years. And it's so to see the evolution and see these very, very complex systems and all of the things that you can do in supermarkets with water reheat and economizer solutions and these advanced higher cost technologies that have been applied. It's great to see these new technologies to be applied to systems that will directly impact the end consumer, where they will see a direct reduction in help offset some of the inflation that we're seeing in today's market, that they can have more money to spend elsewhere because their utility bills are decreasing. So for me, it's a great transition of technology, and it's really been an exciting couple years in the market with higher efficiency standards, new refrigerants, but also the sheer technology standpoint. It will continue to evolve.
Well, I can't top that. So with that, that's it for this episode of EnVisioneering Exchange. And I'd like to thank my guest, Jeff Staub from Danfoss, for joining us.
Thanks so much, Vic. Thanks for having me. I appreciate it.
Absolutely. And so don't forget to subscribe to EnVisioneering Exchange on Apple Podcasts, Spotify, Captivate, or wherever you listen to podcasts. Lastly, if you enjoyed this episode, don't forget to rate, review, and share it with your network. Thanks for listening, and talk to you next time.
This podcast is for information purposes only. The views, information, or opinions expressed during the EnVisioneering Exchange podcast series are solely those of the individuals involved and not necessarily represent those of Danfoss LLC and its employees. Danfoss LLC is not responsible and does not verify for accuracy any of the information contained in the podcast series available for listening on this site. This podcast series does not constitute professional advice or services. This podcast, including Danfoss LLC and the producers, disclaim responsibility from any possible adverse effects of information contained herein. Opinions of guests are their own, and Danfoss LLC in this podcast does not endorse or accept responsibility of statements made by guests. This podcast does not make any representations or warranties about the guest qualifications or credibility. Individuals on this podcast may have a direct or indirect financial interest in products or services referred to herein. This podcast is available for private, non-commercial use only. You may not edit, modify, or redistribute this podcast. The developers of the EnVisioneering Exchange podcast site assume no liability for any activities in connection with this podcast or for use of this podcast in connection with any other website, computer, or playing device.